So, good morning, good afternoon, good evening, where you are in the world. So, thank you again to join us for this next cast talk. Today, we have the pleasure here to have Professor Christoph Bobida from University of Florida, and also Professor José Azambuja, that will be the session chair today. So, the floor
So,
is with you, José.
Ricardo, thank you for the introduction. I would like to start by saying that it's a pleasure to have here the Christoph Bobda as one of our talks in the IEEE CAS Rio Grande do Sul. Christoph was my first research advisor back in 2006, 2007. So I am really glad to meet you again, Christoph, almost 15 years
Yeah.
after our first in-person encounter. This is not in person, but I hope I can meet you again soon in person. So it's honestly really a great pleasure to seeing you here. And just a short CV on Christoph. Um, he's an expert in embedded systems, reconfigurable systems, and systems on chip with applications in IoT, cybersecurity, and in situ image analysis, particularly in hardware software reconfigurable architectures for acceleration of video processing applications at the edge and also in the cloud. So he's a senior member of both ACM and IEEE, and he's also in the program committee of several conferences like DAC, Codes, IEEES, FCCM, FPL, and FPT, and was an ACM distinguished speaker from 2016 until 2020. So he has authored over 200 journals and conferences publications in computer architecture, embedded systems, systems on chip, embedded imaging, robotics, cybersecurity. He also received multiple conferences award, including FCCM Best Short Paper and the SBCCI Test of Time Award. And I know, Christoph, this isn't in your short CV, but I would like also to point out that his latest paper on the future of FPGA, the future of FPGA acceleration in data centers and the cloud in threads is a must-read paper. So let me make this point here so everyone can check it out. So again, Christoph, it's a great pleasure to have you here on your talk entitled Bio-Inspired Smart Infrared Image Sensor for Time-Critical Applications. So, I mean, I've heard a lot about reconfigure applications and so on. This is sure going to be a very interesting talk. So thank you again for accepting our invitation, and you have the floor. Thank you.
Okay. Thanks a lot, Jose, and thanks, Ricardo, for inviting me. So I'm going to be speaking today about one of the core research that we're doing here in my research lab, Bio-Inspired Smart. So it's not going to be more about infrared. It's going to be about CMOS technology, image sensing in general. So we're going to be focusing here on the inference at the edge. So my name is Christoph Bobda, and I'm a professor of computer engineering and electrical and computer engineering here at the University of Florida. And the agenda for my talk today will first be discussing some motivation, providing an introduction about this topic. And that will lead us now to the future of image processing, the challenge that we'll encounter along the way. We'll be discussing our technology, the brain-inspired image processing, how this in-sensor solution is built, and we'll be showing some results and have a conclusion. So why computer vision? Computer vision is one of the most efficient way of sensing. I would say even the most efficient way of sensing. First, it's non-invasive. We don't have to build anything. We don't have to touch and so on. Just remotely, we're capable of getting information about our surrounding, about ourselves. You can use that in robots or to capture the environment. So we have multiple examples of where computer vision can be applied here. Very efficient. The only problem with that is it's very challenging so from the information we're getting from the surrounding to get from the data that we're getting from the surrounding, to get the information we need on time, the knowledge on time, and then under certain condition. So that's where the challenges usually are. How do we sense the environment? How do we get that information from the environment? We usually use image sensor. So image sensor are those tiny devices. Some of them, you can see that here. And those devices has a tiny chip inside, and the chip is just an array of photocells. So they're sensitive to the light, and then they're exposed to the light. And to collect that information, a register is usually used, and the information is read line by line, first stored in a memory, and from there, we will have a processor that will collect the information from the memory and do the processing. Now, the amount of information that we've been having in those image sensors has been growing with the time. So today we're speaking of 4K, 8K. If we just take the 4K, at 30 frames per second, 24 bit per pixel, we need like 7 gigapixels per second, gigabytes of data per second in order to transfer this information from one point to the next one. So it's not possible to transfer this entire information even on a single platform in order to do all the processing. Another project that the DARPA did a couple of years ago, that was the DARPA Argus. So they put a lot of smartphone camera together in order to have a very large image. 72 gigabyte of data was collected with this sensor. So you can imagine that those type of data is what the future that we expect to see in the future. How are we going to be able to collect those data and then do the processing of those data in real time? And this was meant to be mounted on a drone that will analyze an environment and then figure out what is the knowledge in that environment. So pushing the computation in the sensor is the solution going forward. We won't be able to cope with the huge amount of data that current and future sensor, particularly image sensor, is providing to us with the technology we have today. Now, what is the industry giving to us in order to push the computation at the edge? At the edge, we see devices like this, the BeagleBone AI, the NVIDIA Jetson, Google Coral TPU. We have the ST Microelectronics, the Cube AI, and then Xilinx recently released the Crea system on module. We also have the Intel RealSense. But all those devices here are regular processors. They maybe have tuned them a little bit down, remove a little bit of capacity, but they're the same processor we have in high-end environment. We just miniaturize the board that those processors are on. And as proof, you can see that all of them are running with huge coolers. We can use this at the edge. So putting those on a UAV, for instance, is going to consume too much power. So how do we tackle the information at the edge? We had in the past the event-based camera. So the purpose of the event-based camera is not to send all the information we're collecting from those pixels all the time out. We just send the changes. So we build the circuit around the image sensor that will identify the changes that we have in the pixel and then define which one we want to send out. Those cameras are doing well, but the problem is that you still have, you're having the change, you don't have the information. You still have to reconstruct in the back end the whole scene, the whole image before doing this processing. So it's helping, but it's not providing us what we want. The technology we're proposing will allow us to do the inference at the edge directly at the level of the image sensor. So imagine having an image sensor that provides you the way of reading an image like this here. And then what we propose is to have an architecture that could be in form of a single chip, that could be in form of a flip chip, that could be in form of a multi-chip device, but at the edge where the inference would be done in parallel using some of the methods that we believe are the most efficient today. So we're interested in how do we do this inference with low amount of resources at the edge, low power, and as fast as possible. In order to answer this question, we look into the nature. So the nature has usually solved very challenging problem, and then we try to inspire ourselves from nature in order to solve the problem, the more complex problem that we have today. So object recognition, complex scene understanding is done very easily. So you look around, you can know this is a car, that's a house. You know how far this car is from the house. You can differentiate the sky. So it's very, very easy for a human to interpret those scenes. So looking at a scene like this here, we can identify everything that is here very, very fast. I'm seeing a stop sign, a solar panel somewhere. I'm seeing a rocket without having to run a very complex algorithm. When I look at this picture, clearly this is a shopping mall. I look at this other picture here, I know who this person is, even though the image has been completely scrambled, shown in a totally different way here, but I'm still able to recognize that, which a computer will not be able to do so easily. And we're able to do all those here under difficult conditions like lightning, the weather, occlusion, distortion, and we're capable of doing that in real time. So how is the brain solving those very complex challenges today that we're confronted with? And this is what we try to understand in order to apply that. Initially, this research we started was in collaboration with neuroscientists, and our goal was to look at the cue that we have in the brain, understand how the brain performs the very complex task of image processing, and then integrate those here into the technology, so camera. And then on the other side, once we're pretty sure that we validated this concept here, we can use that again to also validate the understanding of the brain. So we make some hypotheses, we verify those hypotheses, and then we send the result back in order for us to confirm that those hypotheses are correct. So looking at the way the brain processes images now, the image comes in the brain and goes through several stages of the cortex where the information is processed there. V1, V2, V3, V4, V5, and then high level of the brain. Along the way, what is happening is that the information is being filtered. So the brain receives a huge amount of information, and then is capable here, going upward, is capable here of filtering the information and removing all the redundancy. So if we look at this approach here, and the brain is capable of doing that very, very fast and in parallel. So it's using a massive field of neurons here in order to achieve this type of task. So we can apply the same if we're capable of building a technology that will take us from the low level of the brain here to the very high level. We don't have to have the same number of layers, but we need to have this hierarchy. And this is what we intend to have in our architecture. We know that the brain processes the image in a hierarchical way. That is proven. So by the neuroscientists, hierarchical, we have on a fast feed-forward computation where the lower level are providing information in a very fast way to the upper layers. And those information become more and more relevant the more you move upwards. But also the upwards provide some feedback to the lower layer in order for them to have some clue about what they're doing. So if an information that we're sending is not relevant for the higher stage, then we will stop sending those type of information. So the brain is capable of filtering redundancy. They're still speaking about predictive coding today, where non-useful information are filtered out and only those relevant information are sent to the high level. And then we have the massive parallelism. So those are the three main concepts we try now to map in our architecture that's going to be brain-oriented, that's going to be low power, that's going to be powerful enough, and that's going to give us the same level of relevance that the brain usually give to the body. So our architecture, therefore, is logically built in 3 layers. The first layer here is the layer that is directly attached to the image sensor, where you have per processor, per pixel, here you have one processor to perform information on that pixel with all the data coming from the neighbor pixel. And the second layer is the region processing unit, where you the region processor plane, where you have processors here that collect the information in region, and then figure out what are the high-level objects that we're finding in those regions. And the last plane here is the knowledge inference plane. So once we have all the clues, then this layer here will assemble that and will try maybe to find object there or do some tracking. So the high-level information. Once again, the input image, what we call the pixel level parallel processing. At this level here, we have one pixel for one processor per pixel. And together, they're in charge of figuring out what are the low-level features in the image. And when we know where those low-level features are, those regions will be selected. And the region that we've selected now will be passed to the next layer that will be in charge of figuring exactly what is that information we're looking for. So our architecture consists of, once we have the pixel array, so coming from the image sensor, our architecture will consist of the pixel level processing plane. And this pixel level processing plane consists of each, what we call the pixel processing unit. So the PPU here, one per pixel. And then right after that, we will have the structure level processing plane. At this level here, we try to figure out what is the structure in the information that we're getting from the low level. Low level, we could be finding corners, line, and so on, or some clues, some features. And at this level here, we put those features together to find what is the structure that we have in the image. And then the last layer here is now to do the inference. We call it the knowledge inference plane. Having all the input data structure, we're now capable of inferring what's the information we have in that image. To implement this, we have multiple options. So the first one will consist of building a hardware that will host the PLPP and the SLPP. Those are very parallelizable units, and we could have them run in parallel. They'll run on the hardware. We could build a hardware infrastructure for this here very easily. And that here could be a chip on its own. So we get the image on a pixel substrate. On the back side of this here, we could put the logic for, or the circuit to perform the PLPP and the SLPP. And then the knowledge inference can go on a processor. So these two parts here will be. And the second option will have everything in a single chip. So we can also just divide these here in two different chips. So we have the pixel level substrate, then we have the second layer here that will do the PLPP and then the SLPP. And the last one, that would be another chip that will do the knowledge inference. So there's some publication out there that claims that the future of image processing is going to be stacked. So it's going to be stacked silicon, right? So you'll have several of those here layer in order to perform those operations directly in the image sensor. Now, looking at the PLPP, how do we build that? So the architecture we have here will consist of one PPU per pixel. And this PPU will take an ADC. Usually when we have this ADC, we still have some space around. In particular, when we're doing infrared imaging, the space is still left around those ADC where we could fit some logic in order to perform some operation. So those space will take the information coming from the PPU. We will have register to collect the value coming from the neighbor pixel. And when we have all this together, each PPU here will be operating. And because all the PPU are working all in parallel, we will have the processing at that level being done in parallel in a much more faster way. So the information or what is taking place in the PPU, what we've implemented so far, were very low-level processing. Like for instance, we have in a smoothing an image here using a Gauss filter. We have an edge detection here, or other type of filter where that will allows us here to find the relevance of that pixel, if the pixel is lying maybe at an edge and so on. And then we also have some module here telling us what is the window that we're currently looking at. Yeah, we're storing previous information and then comparing that with the current one to figure out where we are in this pixel. So what goes out here are now two measures of relevance, right? We have in the spatial relevance here, and then we have in the temporal relevance. So those two here are used in order for us to compute the attention of that particular pixel. Now, once we've had the computation for all the pixels through the PPUs, now all PPU in a given region are going to send the information here now to the RPU. So those are the region processing unit in the next region, in the next plane. And from there, those RPU will take and then will infer what is the information we're getting into this area. Those information could be a circle, could be an arc, could be anything that is of interest for us and that we like to further consider in the higher level. Now, the RPU or the SLPP is made upon multiple of those RPU. The number of RPU here is much smaller than the number of PPU. So we could have like one here for 200 pixels or even more, depending on what the budget is that we like to spend in order to build this architecture. So the value coming from the SLPP will move here in those RPU here, and the RPU part on the SLPP field have multiple RU. It has a controller unit, and then it has a scheduler. So the goal of the scheduler here is to schedule the copy of the data from the RPU here to the bus for the next layer of the processing, the inference, the knowledge inference layer. So the structural level processing gets for data coming, has an attention module, and this attention module gets the data coming from the pixel on a given region. It looks at their temporal saliency and the spatial saliency, and then build a regional temporal saliency and then a regional spatial saliency for that particular region. And now, having that value now, we pass it to the PPE that will perform some other operation, so statistical in nature, in general, looking at the SNR, for instance, the MSC, SSIM, ETP, some other processing that we could perform at the level of this P here to really find what is the relevance of a given region. So you can see that we're moving from pixel to regions, and then we're trying to find the relevance of an entire region. We don't find the relevance of just a pixel. We're really working at the level of a region here because we believe that's more efficient. This is the difference with event cameras that we have out there. The event camera, they work on pixel. They try to find where the difference between the previous value of the pixel A was and the current value of the pixel. If that difference is there or is above a certain threshold, the value is sent out. But the reconstruction of the image is done somewhere else. So it's basically just a mean of transferring less data, but not doing processing on relevant data. Whereas in our case, we're doing processing on relevant data right there at the level of the image sensor. So we get this here, and depending on the value that we are accumulating here, if the temporal saliency or the spatial saliency, if the two here are relevant, then this pixel, this processing unit here is going to be active. So it means that that region has the attention level that we want to have, and therefore we need to keep it active. We need to send the data out in order for it to be further processed. So the data are sent out now just for the relevant region or for the relevant region, what we call active region here, and it will go in the knowledge inference processing. So how do we send the data out? The attention module here tells us if the RPU here is something relevant or not. If it's relevant, we have in a 1. If it's not, we have in a 0 for all the RPU in our system. And then we have our controller, the arbiter, that drives now the write-up on the bus, and the data are copied on the bus, one active RPU here after another. So it goes in the memory of the external processor, and from there, that external processor can use this in order to perform its computation. Now, this external processor, it could be a computer somewhere else, it could be another chip right underneath of the previous one, or it could be even the same chip. If we have enough room, we could have some part of the chip where we have the inference engine here implemented on it. It will make our architecture a little bit bigger, but it's possible. So we run this on several data sets, this concept for the first 2 layers on various data sets with the 3rd layer implemented on a regular computer. And what you see here is the level of redundancy that we have in an image. Usually if it goes up to 70%, and then you could see the error that we were making by considering only those relevant regions and passing that to the inference engine. So the maximum we get in here is something like maybe 5% in terms of performance drop, in terms of recognition. And this is when we usually have a lot of redundancy. If the redundancy is low, we also have a very accurate detection here. But if the redundancy is low, then we're also not saving a lot of power. So our methodology works really very well when we have images that have a lot of redundancy, and that's usually the case, right? So if you have camera fixing certain areas, so it takes time for change to happen in that environment, and the whole time we're just having the same data, and therefore our method will be very efficient here. So here is some tests with real-life application. As you can see, driving assistance here, we divide the image here in various regions, and those regions here are processed independently, and then we can find the road here by combining all those information. Here is a computation that we perform. What you're seeing here at the top is the original video, and you can see the car are being recognized by the regular, I think this was the Euro implementation, where the car are being recognized here very easily. But what you can also see here is that we have a spatial redundancy. So here, a very low level of information, and the car is still being recognized. And in the bottom part, we're still recognizing the car despite having to deal with less than 5% of information sometimes, right? And there, you continue to send in 1% of the image. Here, you're sending no image at all anymore, or no data at all. And here, for the spatial redundancy, you also continue to send in just maybe like 30% of the images. That helps reducing power. Here's another implementation. Still here, another image processing, also used here by a regular machine learning algorithm. And you can see our spatial redundancy here. We are 23%, and then the temporal redundancy gives us sometimes up to 90% or even more. And then we combining the two, the redundancy is a little bit reduced here, but the detection accuracy has not dropped. It's the same like the original detection that we got with the machine learning model that was used to compute to do this recognition. We apply this method also, so working with neuroscientists here, applying this method for what we call the brain imaging, so calcium imaging, where the purpose is to understand the structure of the brain, and they do that by putting a camera on top of the head of a mouse, and then the goal is to take multiple pictures of the brain in various layers. So they scan the brain in those various layers. This is a huge amount of data that you get in there, and those data have to be sent out in a reasonable amount of time. So what we've done here was to emulate or to simulate what we will save in terms of data transfer and computation if our method were used here. So you see the original image, and then our temporal and spatial redundancy, just considering part of the image here. As we perform in the scan, there's a huge amount of data that are being collected there, but the amount of data that we really consider to be relevant here is just a tiny fraction of that. The same for, as we can see here again, we don't have the entire image, but just a couple of points here that we're considering. And by doing that, we hope to reduce the computational requirement. We hope to reduce the power, which is very critical at the edge. The picture here shows us the level of detected redundancy when we're dealing with the image in the calcium. So for the first data set that we had, and you can see that the level of redundancy goes from the lower level 84 here or sometime up to 100%. And in this case here, we're having some level of some cases where we didn't have redundancy in there, but in general, we were mostly in the 80% here. And being at 80% redundancy means that we're performing at a higher level, we're performing the inference here on only 20% or sometimes 15% of the data. That saves a lot in terms of power. Now, how do we do the third layer? So the last layer here, one thing that we agree on, and that is a consensus in the neurology, in the neuroscience community, is that the brain process information in parallel. We have those stream of fast feed forward information from the low level to the high level. The brain is capable of detecting cues from those information and so on. The only piece that is missing, and that nobody really understands how the brain does that today, is the inference. We don't understand how the brain does the inference of information given those low-level data. We've read a lot of papers, there's a lot of publication there, but nobody can really tell us that we understand the algorithm that the brain uses in order to perform this operation. So we as computer engineer, we cannot do that. So we have to work with neuroscience scientists to try to figure out how this works. But for the time being, we like to do knowledge inference. And then we decided in this case here to just go with the the traditional approaches. So the artificial neural network, deep learning that are out there today and that are doing very well. We decided to use that in our inference processing plane in order to infer what information is in the stream of data or video data. So our architecture was tuned a little bit. So now we're having the input image. Then we move here, we combine the PLPP with the SLPP. So within the RPU here, we have also all the PPU, the pixel processing plane. We made those regions here, the first layer of our architecture, for the sake of just making all in a module. And then the scheduler here will send out those regions we believe are relevant to now some region inference engine. So those region inference engine here are in charge of telling us what do we have in a region. Those region inference engine are basically some deep learning component that we've implemented. And those deep learning components, they have two convolutional layers here, and then they have a full connected layer. In between, we also have some configurable data path that we're using in order to make that happening. And having all these here, we can attach an ROIC, and this ROIC will just collect not only the pixel, but will also collect the knowledge. So what is that we're seeing in the image? Or we could just decide to collect that knowledge and just focus on the area where those knowledge are coming from in the image. Or we collect both for the sake of maybe correctness, so proving that the method is working. So it's up to the user to decide what to do with that. So the mapping to the high level is done using those convolutions. So 2 layers here. And those 2 layers are usually the most challenging one. And those 2 layers will perform and will have the fully connected. That will do. That will be the last one. And this is also where we have the less challenging thing to do. So the region inference engine here is nothing else than for now. So if the neuroscientists tell us tomorrow, this is the algorithm that you have to implement there in order to infer the knowledge from that region, of course, we'll be glad to reconfigure our architecture and then implement that instead of having this deep learning component. So our architecture have to use a C1 and C2 module here to perform those 2 convolutions, and then use the fully connected network here in order to do the rest of the work. So that way, we have what I've previously explained. So the RCU module, RCU, and then in between, we have some input buffer. Those two modules here work with coefficient that needs to be stored in a memory. We use an external memory. Even if you have a system on chip, you still have to put a memory somewhere. If a single chip would have to be mounted either on a very tiny board, or you may decide to have internal memory to that chip. So all is a matter of how this technology is being implemented. The RPU architecture collects the information coming from the PPU here, and then and then use them in order to perform those convolution at this level here, and to generate the data for the first layer here that will go into the next layer. And we do in this pair here. Let's say if we have a 16 layer, for instance, or 13 layer, like we have that with BGG, 13 layer CNN, then we'll do the pairwise mapping to those two layers here, and the last layer will be mapped to the second one. So it's not that we're using the two layers here and that we're limiting ourselves to just two layers CNN. We can do more than that. Now, the architecture of the RPU that perform the part of the RIE that perform here, the region inference engine, consists look like this here. This is the architecture. We're having a FIFO of data, the weight, and that goes here to the fully connected layer, so the control unit, and then the FIFO, the logical layer that we know. So in any convolutional neural network, is usually how it looks like. And here we have the implementation using some multiply accumulate unit, shift register, weight buffer, in order to perform those convolution. So this is how the internal architecture looks like. And now having the pixel level processing plane, the structure level processing plane, the knowledge inference processing plane, the knowledge inference plane, how do you put all that into an image sensor? That's what we would like to have in the end. Having an image that comes in, our pixel level processing plane here will be in charge of performing the information, figuring out what are the low-level clues that we have in a region. And then we'll send only those regions here that we can consider. The SLPP will take those regions, will further reduce them, and will have only those regions here that are relevant. So we're having an attention base, and those that have the attention score pretty high are the only one that we will be sending out. And then the NIPP here collect those data and perform the recognition. What is the data we're interested in here? Yes, the three are relevant, but which one are we interested in? Maybe this one, and that's the one that is selected and sent to the ROIC. So we're speaking here of a novel class of image sensor with a novel type of ROIC, where we have some computation between the image sensor and the ROIC circuit. And once we agree that this part here is the one we want to send out, then we also have some communication between the ROIC here and the PLPP directly. So the PLPP could be sending all pixels here to the ROIC, so that when we send this part out, we still have our image, right? It's not like we just want to send this part out and nothing else. We still have our image. So we use this here to be able to send all the data as required by the user to the host, and the host will decide what to do with those data. Now, the two here could be on a single chip. The three could be on a single chip. We could have these two here on one chip, and that could be in the back end. So in that case, we just pass the information that we need here and the reconstruction, and the inference will be done on the host. So now we did implemented this architecture in two ways. We did that in FPGA, and we do that in ASIC. So in FPGA, we used, so I was the Xilinx FPGA using the tool, the Vivado design suite. We also did that with Quadus Prime from Intel, but we implemented that only in the Vertex UltraScale Plus from Xilinx. And then in ASIC, we used the design compiler tool or the design suite from Synopsys, the DCS design compiler, Innovos, and the PrimeTime in order to implement our design here on a TSMC standard cell technology with 90 nanometer technology. So the PLPP, we made it configurable. The purpose of having it configurable was it allows us to explore various implementation of low-level algorithm in the processors. The same for the SLPP here, and the same for the NIP. The architecture making it configurable means that at runtime we could decide we want to use a different infrastructure than the one we previously had there, maybe because our data is showing some pattern that is better off with this particular technology, right? So this is what we've implemented there. And the reconfigurability is done, let's say if we take the case of the RPU, is done here by being able to, the processor here implement various type of processor algorithm, various size of data, all that in those different processors here, and then just being able to select one at runtime. So as you can see here, we have various implementation. Because we having all these pre-implemented on the chip, it consumes some area, and it took us, it makes the design becoming very, very large. But we're thinking going forward to maybe have the same type of implementation FPGA does, like just reconfiguring those parts here using active memory, like lookup tables, in order to reduce the footprint of the chip. So the attention module in the technology I explained previously gave us a 142 square micrometer, and then here the power consumption of 0.127 milliwatt. And then the yeah, we also had a crypto module once we knew that we're gonna be sending the data from the SLPP to a host module. So we implemented the crypto there to make sure that the data was secure. It's not, it doesn't have to be part of this architecture, but we just put it in there. And so this is the analysis and the implementation on the FPGA. On the FPGA, as you can see, we have the APL module. So the attention plane here, we have the first convolutional layer. The second convolutional layer was the first and second convolutional layer was implemented here, and then we had the fully connected layer. So after some optimization, this is what the architecture gave to us, and this here was for a 64 by 64 image. That's not really huge, but imagine that we're having a field of maybe 1000 by 1000. So we'll have to run that through this architecture here by the number of time 64 by 64 will be found into that bigger image. So we still have some level of parallelism there. We didn't do all the optimization here. As I said, we had all potential algorithms that we like to consider implemented in those RPO, which consume a lot of room. If we were to reduce that, then we may be able to increase the size here, maybe to 250 by 250, or even move it to the level of a VGA image. So as you can see here, the resource consumption lookup table, 154,000. That's pretty big, yeah, for an APL and having a 64 by 64 images. Number of flip-flop here for the memory, DSP0, and then the power consumption. Since we're using some, we're using no DSP here, everything will have to be implemented using those lookup tables. And we're speaking here of Mac. So Mac consume some amount of space. So if we found a way now to maybe have those DSP here be more active, then we can reduce those size here considerably. But our target architecture was not really an FPGA. So we looking to have dedicated chip that will be able to be append right after the image sensor in order to perform this computation at the edge. And the ASIC implementation is given here. We have in the attention plane, and then we have in here the knowledge inference plane here. We use 4 of those modules here, 4 of those, and that can also help us schedule a given number of regions. So it's unlimited in this case here, and then a fully connected layer. So this was the ASIC implementation, and we can look at the size, like the APL. The inference plane here is the biggest one, almost twice the size of the, almost twice or almost four times the size of the APL here. And then we have the first connected layer, the second connected layer that is not showing here and having the size given there. And finally, the fully connected layer that is the smallest one. The power consumption is also provided here, depending of the internal power, the switching, the leakage, and then the total current. Now, as we can see here, depending on the amount of redundancy that we're having in our image, the percentage of power and then the execution time goes considerably down. It's almost linear. The more redundancy, that's logical, right? The more redundancy, the lower the relevant data and the lower the power that you need to spend in order to do the computation. Also, the lower the execution time you have to spend to do that computation. And some more data here. We run this here on the LINET 5 here, and we're able to get up to 87% power saving due to redundancy of information. And then we had like 58 times speed up of the state-of-the-art implementation, right? So the state-of-the-art implementation is provided here, and then you can look at our implementation with the convolution. So 160 microsecond, whereas we're doing only 2.74, doing a lot in parallel, even if we have to schedule on the convolutional computation block 1 and 2, schedule there multiple times. The fact that we're still doing that in parallel have a huge impact, and the fact that we're doing that on just a fraction of the data has a huge impact. So the accuracy of our algorithm did not decrease by just considering those relevant data. You see that we're having 98.8% here, whereas the state of the art is having 93% on the same data set, right? And here the VGG also, again, we did some dynamic adjustment of the MAC operator here. I won't go into detail of that, but we were getting like almost 4 times the speed of a GPU with 28% less energy consumption than the state of the art, and also 45% energy efficiency. And sometimes if we had like 90% of irrelevant region here, then we can have another 35% on top of that. So it helps really focusing on those relevant regions, and then defining an architecture that will be able to detect those relevant regions and then help us now improve our architecture. So this is the end of my talk, and I'd like to summarize quickly. We were able to provide the motivation of moving the computation at the level of the image sensor, and we pleading to have a stack technology that will allow us to have image sensor, IC devices to perform early visual features and knowledge inference right there in the sensor. But in order to do that, we can't just compute on the whole amount of data. We try to mimic the brain, and we look at how the brain processes information. It's hierarchical, it's parallel, we have some feedback, and then we try to remove as much redundancy as possible. And having this redundancy being removed, the algorithm that we've implemented for that was predictive coding in time and space. And then we use some statistical method to help us define what region was important. And that allows us now to reduce the amount of data. We were able to provide the best speed up that we believe is out there, while even maintaining the same level of accuracy than the state-of-the-art algorithm. So that's it for my talk today. Thank you very much for listening. And if you have any question, I'll be happy to answer. Thank you.
So, Bobda, thank you so much for your great talk. While we wait for some questions on the chat, let me invite our audience to subscribe to the YouTube channel if they haven't yet, to get notifications on future content and to get access to all the videos that we have already uploaded. I have one question.
Yes.
But first, I would like to thank you, Christoph, for your great presentation. So, actually, my first question is more like a broad question, because you work from the edge to the cloud to the data server and so on. So, my first question is, ideally, we want to process data where data is. Right? We want to minimize sending data from one place to another one to process data. So ideally, we would like to process every single data on the edge and then send results to the user, right? But that is not always what happens. Sometimes we don't have enough hardware or something like that, and we have to use the network or send this data to a data server where we can process it. So my broad question is, what are the pros and cons of processing data on the edge or sending it to a data server? And of course, I am of course considering your work here, the work you just presented, where you try to process data on the edge instead of sending it to a data server and process that. So could you comment on that?
Yes. I mean, the pros of having to do the data at the edge is that we could sense much faster. We could process with much higher frequency on a large amount of data. If you're having an image sensor that gives you, like, let's say 7 gigabyte per second, so you have to define at which frequency will you sense that environment. If we were able to do the processing very fast and send only a fraction of the data out, we could be sensing with a much more higher frequency, moving us from the digital even close to analog, right? So being able to have thing being sensed continuously, which we're not capable of doing today. So it's always an advantage to have the inference right there where the data are. The only problem with that is the resource that you need to spend in order to achieve that goal. And we don't have those resources today. So it's very difficult to have those implementation. Our work is one contribution in this direction, where you want to put those resources in there, but it will also increase the price of the image sensors. It will increase the prices of even though we're reducing the processing speed and we're reducing the power consumption and so on. This is the power consumption on the computation. This is not the power consumption of the regular sensing. That still add up to this image sensor, and it becomes a problem, right? The resource, the infrastructure that you need to put to make that happen, that's the drawback of moving things at the edge. Having them in the cloud, you have to deal with many things. In the cloud, you have to deal with, if you're collecting data, for instance, data about people, their privacy and so on. When you start sending those data to the cloud, the issue of breaches, for instance, security that you need to provide, and also communication. So you need to have enough bandwidth to do this computation in the cloud. Today is not a problem because we have all that, but that infrastructure must be there. The cloud has its own delay. It's always better to go at the edge. You can keep the privacy right there. You can just sense and discard those data that you find not interesting, and you could send only the knowledge out. But the cost of doing this here for now is relatively high.
Yeah, and I believe that in your application, for example, as we are talking about mainly Internet of Things, transmission can be costly, right? I mean, you either have a wireless access where you have free data,
Yeah.
or you need to pay something like a 4G now 5G, and that could be expensive. I believe your application, by reducing the size of the image, can decrease this cost, maybe even allow some transmission over GPRS technology or 5G or something like that. But still, the price for deploying a UltraScale Plus can be quite expensive also, right?
Yes. So the UltraScale for us that's the prototyping, right? So you start there, and right now we're starting to work in the optimization with other student of mine. We're now pushing into how can we make this architecture more efficient? How can we schedule the stuff in those? Is it possible to even look at some part of embedded FPGA using some configuration to improve the efficiency of these computations? So we're thinking of all that now. But we believe, and not only us, if you just type stack silicon image processing, and then you'll see a lot of publication out there, all of them claiming that the future of image sensor will be stacked silicon.
I see. We have one question here, Christoph, actually two of them, from TZZZ. I'm not sure if this is his name. I don't think so. But anyway, he says, let me add to the stream here, and I'll read the question to you as well.
Okay.
So the question is, do you have a specific kind of application in mind, like surveillance cameras, or maybe for a long time nothing happens, like a warehouse, or a lot happens, crowd on the street? And this is, let me just complement this question. Your examples here are mostly like one or two cars, because I think it was from like a surveillance, like a shopping mall surveillance camera, or like a surveillance camera, like a traffic camera, right? But
yeah.
Would that work as well on a moving car where you are constantly having new images and so on? This would be a new problem, right?
It works. So we took state-of-the-art data set and model and run our algorithm there, and it works. So it just giving us the same, 90% accuracy compared to what we have out there as state-of-the-art. And whereas here we also just working on a fraction of the data. And another important point of this is that we've been dealing with how do we do sparsity on data in the cloud, for instance, in order to train the model. And so this approach also helps you even do that sparsity, knowing that the data that you currently, the redundancy that you're currently removing is a redundancy that is a true redundancy. So it's not really something, you're not discarding important data, right?
Yeah.
Yes. And then just focusing on that one, make your training much more faster, so we have I didn't mention that here, we have a simulator. We call it's an event camera simulator, but our simulator operate on region as opposed to those simulator that works on pixel. And you can download that from our webpage, and you can run all kind of algorithm there. Our algorithm is implemented. You can take any application, deep learning application, and you can see what our algorithm will provide to you. It's in that simulator. You can also even capture the model of an image sensor and enter that in the simulator and work with that in order to have the whole end-to-end processing chain from the image sensor up to this inference engine.
I see. And this is actually Tiziana, so the person asking the question here. She also has a second question about data security. So according to about encryption and due to GDPR, for example, how do you handle this? I believe you have a encryption module, right?
We have an encryption module in there. We put it there because we wanted to consider security. It was not necessarily part of this this architecture technology, but we decided to put it there. And it also didn't add much in terms of resource. It's a tiny crypto core. And before sending the data out, we encrypt everything, and then we get that on the other side and decrypt the data.
Perfect. I have also another question from Umboa, I believe. I'm sorry if my pronunciation is not really good. And the question is, thank you for the talk. Can you please highlight some future scope for this work?
Future scope is now we're trying to get. So we've been funded by the NSF, the Missile Defense Agency, as you can see there, and so through various mechanisms. So now we're trying to get the level of funding that will allow us to realize this here now on a real IC device. Also working with a colleague here who's an expert in image sensor in infrared, and we have a small facility here at the university where we intend to do like 10 by 10 patches and then put many of them together to demonstrate our technology, first with an FPGA, but also with a dedicated chip. So we're looking for funding in order to make that happen. So that's our future work. So a live demonstration, and then this implementation of a prototype, and then we'll continue from there. But this is a type of technology that requires huge investment in order to make that happen.
Sure. And then you would move from an FPGA solution to an ASIC one, right?
We're gonna be doing, yes, we will be doing an ASIC, yeah.
And then it would be,
yes.
but in this case, the inference engine would be on the data server.
We not necessarily. We can have it on another processor. Like
okay.
Yeah. Okay. You another case, if you look at the tank, for instance, they're having infrared camera in there, and those infrared camera have to identify what the enemy in front, analyze the scene, and then detect quickly what are you seeing? Is that an enemy, and so on. And through the war in Ukraine, you see how important it is to quickly recognize where the threat is. And now that inference part, you're sending it out to another processor still in the same, and they will send the target there and then make the decision where to hit. Right.
I have another question here, Christoph. Let me add this to the stream. Do you think additional layers should be deployed to expand pattern recognitions on the field? This is a question by Guilherme.
Additional layers where? You mean in the region inference engine? Because there we have 2 layers, but we can do as many layers we want by mapping them to those 2 layers and then just keep doing that. So kind of rolling over, right? But if it's the layer, the number of layer, like the pixel level, then the region level, and then, so I think we find with those 3 layers for now. If needed, we could look again in the brain. I know the brain has, just for the cortex, they have like maybe 4 or 5 different layers in the brain for just the cortex, or the image cortex.
Oh, okay. So let me make a last call for questions here. In the meantime, let me thank you one more time, Bobda, for your great talk. Let's see if we get some last minute questions here. But the work is really interesting. In my opinion, I believe the next step is actually doing the chip to reduce costs and everything, and then target to specific applications. I believe you have a wide variety of applications to apply this work for, and choose, target, and deploy on the field and see what happens. I'm sure this could be very important for society as well, and for many applications.
Absolutely, yeah. By the way, I'm looking for a PhD that has some knowledge in IC design, exactly to work in this project.
Perfect. We have a couple here. We have a couple of students from.
Yes, send me the CV.
I saw here on the list quite a few students from the microelectronics postgraduate program.
Mhm.
They are mostly for master students, but we have a couple PhDs here. So I'm sure they can find you, Christoph, on your webpage, on your
Yes.
University of Florida
Right.
personal webpage.
Yes, the address is here. You can.
Let me
So
check.
smartsystem.ece.ufl.edu.
Perfect. So let me invite our IC designers and our audience that wish to work in this project with Christoph to give him a call, send him an email, and see what can be done. So Christoph, again, thank you so much for your talk.
Yeah, no problem. Thanks a lot for inviting me. I really enjoy it, and it was nice reconnecting with you after so many years.
Yeah, I believe almost 15 years already.
Right. Yeah, we'll have the chance maybe to visit you in Porto Alegre. We've been having a great connection down there, but I've always been in the north, yeah, or in Rio.
Yeah, yeah. Porto Alegre is kind of different from Rio and the rest of Brazil, but it's a really nice city as well.
Right.
And you have an open invitation about it. Just let me know when you're arriving, and I'll pick you up at the airport.
Okay, sounds good. Yeah, we'll discuss that in a part 8. Yeah.
Yeah,
Thanks.
Christoph, let me just talk about our next talk, our
Mhm.
next week talk.
Okay.
Sergio Bump is he's a colleague of ours in the Federal University of Rio Grande do Sul. He says URGS has great students in the microelectronics graduate program. They are seeing this video. He thanks you for this talk. As does Tiziane, she asks, she will write to you separately, so she will probably send you an email soon. We have a couple thanks here from Guilherme and so on. So Christoph, for the last time, thank you. It was a pleasure having you here. And yeah, I think that's it. I'll see you soon. So
Thank you. Thanks a lot. So I'm gonna leave the studio now, and I'm looking forward, for further work with you. Okay. Bye.
bye bye. It will be my pleasure. See ya.